All right. Good morning, everybody. Welcome to Honors Chemistry. Today is Wednesday, May 20th, 2020. And today we're going to start learning about equilibrium. We're starting a next unit. I actually have, I'm planning on just covering one unit a week for the next 4 weeks. So, or I guess 3 weeks. Yeah, we only have 3 weeks left. So, you just finished kinetics. You took your quizam yesterday, and I'm planning on giving you guys just a quizam once a week, just a little something. I hope it didn't take you too long to do that yesterday. Just a little something to work on that every Tuesday on what we covered the previous week. So we'll meet today and Friday, and we'll talk about equilibrium. I'll give you a little bit of a review. If nobody's been emailing me with questions, so I'm assuming that it's making sense if you don't have questions. But if you need more practice on anything, or if you just have a simple question, please don't hesitate to email me. My varsity chemistry students were emailing me all the time before their AP test last week. I was getting emails 24/7 from those guys. So really, I don't mind answering your questions. As a matter of fact, I'm thinking about starting to do an office hours on Mondays. So maybe I'll let me look at my schedule on Monday. And oh wait, no, Monday's a holiday. Never mind, not on Monday. Maybe in future Mondays. I know there's not that many, but I'm thinking about starting an office hours where you guys can pop in and ask me a question if you have any. But anyway, until then, just don't hesitate to email me if you have questions. I'm trying to assist you and give you knowledge from afar, but I know this stuff isn't easy, and I'm trying to give you all the keys and the tools to do so. But I'm sure that some of you have some questions, but don't hesitate to reach out. Anyway, we've got 3 more units to cover. Okay, so we just finished kinetics. By the way, those tests, I'm going to grade them as soon as we're done today. I'll get them back to you this morning. Okay, so you will get your responses back on your test. If you have any issues with the way it was graded, don't hesitate to say anything. I'm also still working on your Alka-Seltzer labs. I loved watching what you guys uploaded onto YouTube, or onto Instagram. Well done. I'm still working on grading those. I thought I would be able to get through them pretty quickly, and I started them, but I haven't gotten through them. So I still have to grade your kinetics, quizam, and your Alka-Seltzer labs, and I'll get those done today. That's my plan. This week, we are starting equilibrium. I'm going to cover this today and Friday, and then you'll have another quizam on Tuesday on equilibrium. And then we're going to get into thermochemistry. And thermochemistry is kind of fun. I have a fun kitchen lab for you guys to try with that one too. And then we'll do a little bit of acids and bases the first week of June, and then that's it. We're done, okay? And I'm really just teaching you for exposure at this point, not mastery. I just want you to, once we get to AP chemistry, I want you guys to at least recognize some of these things that we've already done, okay? So that's my plan, is just expose you to these last 3 topics of chemistry for the rest of the year. Now, some of you have been asking me about the final exam and what's that gonna look like. To be honest with you, I don't feel comfortable writing and giving a final exam in a digital learning situation, just because, I mean, it's completely open note, it's completely open web, it's completely open friend. There's absolutely no way for me to verify the integrity of the fact that you are actually taking that test. And so here's what I've decided to do. I've decided to slightly alter my syllabus, and I'm going to say that if you are happy with the grade that you have at the end of our at the end of our units, I'll probably give you a quizam on the next 3 topics, right? So we'll get an equilibrium quizam, we'll get a thermodynamics quizam, and we'll get a acids bases quizam. And if you are happy with your grade after all of that, then you don't have to take the final. And many of you are probably kind of have an idea. Most of you have been holding a pretty steady grade throughout the whole year, so you probably have a pretty good indication of what grade you're going to have in 3 weeks. Okay. But I want to keep you engaged, right? So I want to keep you coming to these Zoom classes and actually learning. So if you're happy with your grade, then you can keep it. And if you want the opportunity to do an extra assignment to help boost your grade, then you can. And that assignment will be an explainer video, very similar to what you watch with Mr. Anderson videos. And so that explainer video would be uploaded onto YouTube. Okay, so it would be something that's published, and it's going to be on my YouTube channel. And so I will give you that opportunity to improve your grade. I know your next question, how much can it improve my grade? Well, it can improve your grade by 2 levels. So if you decide to do that final project, if you have a B, it can move you up to an A-. If you have a C+, it can move you up to a B. Right? And so it can go 2 levels, not a full grade jump, but just 2 jumps. Okay. So maybe that's your motive to continue, the motivation you need to just keep working hard, do the best you can on those next few Quizams. I am not going to drop your lowest test score from this quarter because we did not take a quarter exam. So I'm not going to drop the lowest test score. Plus, you guys, everything's open notes. So I figure that's kind of an easy trade-off. So anyway, that's what the rest of the year looks like. Okay. Final is optional. Okay. If you like your grade, you can keep it. And if not, then I'll give you an opportunity to do an extra project. Also, I hope you noticed that yesterday I put something up on the stream. If you're looking for a good show to watch, then I would recommend that you watch the Poisoner's Handbook. It's on sale for a rental at Amazon. And if you want to watch that and write me a little paragraph about your favorite chemical mentioned in the movie, I'll give you guys some extra credit. And for some of you, that might be what you want to boost from an A- to an A, and not have to do that explainer video project. Okay, so that's another little extra credit opportunity that you have. Okay, but it costs money, so I can't force you to do it. So it's extra credit. All right, guys, let's go ahead and take a peek at the agenda for today. Okay, so today we have molecule of the week, and then we're going to look at a little demonstration I filmed in my classroom before all this was over on Le Chatelier's principle. And I've asked that you print out this or access this demo so you can follow along with us. Okay. And then I have some equilibrium notes for you. And tonight I'm going to upload 2 worksheets I'd like you to work on for homework. I'll put the answer keys to both of them. And they're just reviewing the ideas that I'm going to bring up in the notes today. Tomorrow, I'm going to post a few demos for you to watch and a Google form for you to fill out. And then I have a simulation for you. And then on Friday, we'll come back together, maybe do a little extra practice together and review any questions you have for the week. And then I'll give you some review and we'll have a Quizam next Tuesday. Okay, let's go over to the Google Classroom and take a look at these things that I've uploaded for you. So I started a new topic here, Unit 10, Equilibrium. This Le Chatelier's principle activity is what we're going to look at early on today. Okay, and it's short. You don't have to fill it out completely, but I'm going to ask you to make some predictions. I'm going to ask you to make some observations, and this might be helpful for you to have nearby. Okay, so there's that. And then I also uploaded the notes. These are the notes we're going to be going through today. So you can write things down in your brain book, or you can just listen and take some notes in your brain book as we go. It's totally up to you, but you have access to the notes that I'm giving you today. And then this simulation is another one I'd like you guys to try. It's another one of these those PHET simulations. And I just went to go download it this morning. Unfortunately, you do have to have Java for it to work. So it's similar to that last one. I think all but one of you were able to get it to work on your computer. But it should be pretty straightforward. And I just want to show you the simulation real quickly. You are going to have to update your Java to do this, even since the last time we did a simulation. I went to go download it this morning and it said update your Java first. So if you have Java on your computer because you ran the last simulation, then you have to go and update Java first, and then go to the PHET website. So when you Google search PHET, make sure that you go to this website, the PHET Colorado website, because there's other ones here, like the Cengage one. I tried to go there first and it wasn't working. So make sure you go to this site. And when you download it, you might have to go into your security settings again and tell it it's okay to open it anyway. It's not going to harm your computer. Anyway, once you open it, here's what it's going to look like. And I'm going to reset everything here just to show you what it'll look like when you start. Okay, so what you have is this reversible reaction, A going to B, and you can adjust the height of these walls, okay, by just dragging them up and down. You can you guys see this screen, by the way? Can you see the simulation? Can anyone tell me? Yeah, you can see it? Okay, thank you. I wasn't sure. What you can do is add molecules to the container. So I can say add, I don't know, however many it asks you to do, 50 molecules of A. And then I can push start. Uh-oh, I did not work. Come on, simulation. Let's see. Uh-oh. Well, let's see. Oh, I have to push play down here. There we go. Okay. And so the first thing I'm going to have you guys do is do almost like a timed experiment where every 20 seconds you're going to stop this and you're going to record the number of molecules of A and B. Now, if you probably noticed that this looks really similar to an energy diagram, right? Where I can have an endothermic reaction where the products have more energy than the reactants, or I can have an exothermic reaction like this, where the products have less energy than the reactants. So this blue line should look really similar to the energy diagrams where they had a certain activation energy. Now you'll notice these molecules have almost no kinetic energy right now. So I can add heat to help heat them up, right? And get them to move around a little bit faster. Or the other thing you can do is just reset this whole thing and say, when we add the particles, we want them to add at a really high temperature, right? Like maybe I'll put 50 particles in here and then start. And then see how much they're bouncing around so much. And essentially what's happening is A is going to B, but then the molecules of B can also turn back into A. And so every 20 seconds, you're going to either pause this and record the total numbers of A and B, which are given right up here, okay? And then you're going to graph that data. And you're going to look and see what it looks like once this reaches an equilibrium from a graphical perspective, okay? And then we'll talk about that more on Friday. If you have issues opening the simulation, let me know, but it's going to be really similar to the way you opened the last simulation. Just remember that you have this pause button down here. That's going to help tremendously to take data points every 20 seconds, okay? And obviously this seconds is sped up. You don't actually have to wait a full 20 seconds. It's in fast time, if you will, okay? All right, so that's the way the simulation works. It's actually relatively simple compared to some of the others that we've done, but it gives you a nice visual of things that we're going to discuss today. Okay, and so that's pretty much what we're looking at for the rest of the week. Don't forget to check in on the attendance sheet today too, please. All right, so let's begin with molecule of the week. I don't know about y'all, but I was pretty darn excited that they opened up the beaches last weekend. And I found myself and my kiddos went to the beach. See, we went to the beach 3 times over the weekend. And then yesterday we went to the beach again. The kids are loving it. They finally have a place to play. And so I'm sure that many of you are hitting the beach too. So I wanted to remind you to wear that sunscreen. So the molecule of the week this week is something called insulazole. And the chemical name for this is a tongue twister. Let's see if I can say it. It's phenylbenzimidazole sulfonic acid. And it's a common ingredient in sunscreen, but more commonly even in cosmetic lotions. So a lot of times they have SPF included in a face cream. I put one on every morning. You should too. So that way you're automatically wearing SPF every day on your face. Protect that nice young skin. Anyway, it's very commonly used in those cosmetic lotions, but you might find it in sunscreens as well. But it's really good at protecting against UVB rays. So I want to remind you that, remember the electromagnetic spectrum, where we have the visible light, Roy G. Biv, right in the middle, and then just outside of violet was ultraviolet, and that was higher energy than violet. So UV, ultraviolet rays, are higher energy, which means they have a greater frequency, lower wavelength. Lower wavelength, greater frequency. And that means that they can cause damage to the DNA in our skin cells and cause skin cancer. And so the UV part of the spectrum is actually divided into three parts. There's UVA, UVB, and UVC. So certain molecules are really good at absorbing or reflecting different parts of the UV spectrum. So this molecule is really good at reflecting those wavelengths in the UVB range. So that means that we're going to have to combine it with other molecules that are good at reflecting UVA and UVC to get a full spectrum of UV protection. So other molecules that are good at protecting against UVA rays would be avobenzone, titanium dioxide, zinc oxide. Sometimes you see people put that on their nose. And so I just picked up my sunscreen yesterday and started looking, and I think this molecule, avobenzone, was in there. So look at the ingredients, see if any in your sunscreen, see if anything rings a bell to you. Anyway, the interesting thing too, and then I want to remind you of, is that when you're formulating these sorts of things like sunscreens or cosmetic lotions, not only do these molecules have to be really good at reflecting the light, that the UV light, to protect our skin, but also they have to be water soluble, right? Remember those solubility, and we just talked about what makes something good at dissolving versus not. Look at these oxygens. And the OH group right here, that can form hydrogen bonds with water molecules, which is why it's soluble in water. And so since it's water soluble, it's perfect for lotions or sunscreens. But the other thing we have to think about when we're formulating some sort of a sunscreen is environmental toxicity, because we're going to put the sunscreen on our bodies and then you're going to go splash around in the waves, right, and play. And we want to make sure that the chemical is not going to have harm or cause harm to the ocean ecosystem. Okay, so you also have to look at environmental toxicities. So when we're formulating these things, and this is all chemistry, right? These real chemists out there in the world have to think about, how are we going to make a new cosmetic that will block against the sun, but it's also going to be water soluble so it feels light on the skin, but it's also got to be something that has low environmental toxicity. And so there's lots of different things that go into formulating a new product like this. Okay, so wear that sunscreen. That's my message for you this week. All right, next up, let's take a look at this demonstration. I want to look at the Le Chatelier's principle activity. Okay, so if you would please access this, and if you could just take notes somewhere, or if you printed this out, you can write directly on it, whatever works best for you. But I want to introduce the concept of equilibrium to you all with this demonstration. Okay, and the purpose of this is that you are going to use the scientific method to investigate something called Le Chatelier's principle. Okay, Le Chatelier's principle. That's kind of a fun one to say. I'm going to give you guys one guess. Where do you think this scientist is from? Le Chatelier probably, yep, you guessed it, France, yeah. And it's kind of fun to say, so let's just say it, whether your mute is on or not. On the count of three, let's all say Le Chatelier together. 1, 2, 3, Le Chatelier. Right? It's kind of fun. It rolls off the tongue, right? So Le Chatelier's principle is something we come across quite often in chemistry. It gets applied to not only equilibrium, but also acids and bases, which we'll be covering very soon. And we're going to analyze these some shifts in equilibrium using color changes. Okay, so I have this reaction here, and it's a net ionic equation, but I realized that my superscripts became subscripts. I'm not quite sure why that happened. This should be a superscript of +3 and a superscript of minus. These are the charges on these particles, a superscript of 2+. So you can adjust that if you have it in front of you. This is a net ionic equation that we're looking at, okay? And so what we really had, I'll show you on my board back here. I'm gonna stop share for just a moment. We had potassium thiocyanate and iron nitrate. So, pin my video, you guys can see me here. So really what I did in this, what I'm going to do in this demonstration for you is we're going to take something called iron nitrate. I think it's iron 3 nitrate if I'm not mistaken. And it is, I don't know if you guys can see, hold on. And it's aqueous. Okay, and we're going to combine it with potassium thiocyanate. And it's aqueous. And we end up with iron thiocyanate that has a +2 charge and potassium nitrate, and these are aqueous. Actually, the iron thiocyanate, I wonder if I should make this a solid. It turns into kind of a reddish solid color. Okay, and so what I want to do here, if I write a net ionic equation, the iron and the nitrate break up because remember solubility rules, nitrates are always soluble. So we get iron 3 plus 3 nitrates plus potassium plus thiocyanate yields iron thiocyanate plus, and then potassium nitrate is very soluble, okay? And so the nitrates, I know my equation's not balanced. Shame on me here, I can do this. No, I don't know. Here, I'm not even gonna worry about balancing it. This is not the point of my I don't wanna waste our time here. But you'll notice that these are spectator ions, right? So they're not included. Okay, and that's why I only have the iron thiocyanate and iron thiocyanate, okay, and that's what we're playing with. But the interesting thing is that this reaches an equilibrium. And this is the first time you guys have ever seen an equilibrium. Equilibrium means that the reactants can form products, but also the products can reform the reactants. So the first time ever we've seen a reversible reaction here. Okay, all right, so let's go back to that. Okay, so you'll notice that it says here that I'm adding more iron 3 nitrate, or I'm adding more potassium thiocyanate, or adding more potassium nitrate. That's just because those are the true reactants. Those are the source of iron and the source of thiocyanate. But we're just really exploring this net ionic equation, okay? And then this is something called sodium hydrogen phosphate. Okay. All right, so let's start by making just a couple of predictions. So we know that, why is it that I can't draw on this? There we go, my annotate function. Okay, so iron ions, these guys are gold, okay? And then my thiocyanate is colorless, so I'll make that just black. Okay, this stuff is black, or colorless, not black. And then this substance, this iron thiocyanate, is red, okay? So I just want you to make some predictions here, just for fun, okay? Predict what would happen. So we've got this substance now, that this solution that's at equilibrium. It's got all three things in here. The reactants are formed products, the products are reforming reactants. So I have all three of these together, and it's kind of like an orangey color, to be honest with you, which is not a surprise, right? And I just want you to make a quick prediction. What would happen to the color if we added more iron, if it were more gold? If we added more gold, do you think it's going to get more golden? Do you think it's going to get more red, right? So if it's starting at this kind of in-between orange color, if we add more of the reactant, more gold, do you think it's going to get more gold? Do you think it's going to get more colorless? Or do you think it's going to get more red? And this is what scientists do. We just make predictions, right? So just write something down. There's no correct answer. Okay, and then predict what would happen to the color if we added more thiocyanate. If I added more of that colorless thiocyanate. So if I added more colorless thiocyanate, what do you think is going to happen? Do you think it's going to get more dilute, like less orangey, like more you know, a less vibrant color? Do you think it's going to get more red? Do you think it's going to get more gold? What do you think it's going to happen if I add more thiocyanate? And then lastly, dihydrogen phosphate. So this dihydrogen phosphate is the part here. This is dihydrogen phosphate right there. Okay. It's an ion. It's just, the sodium is just there to make it soluble in water. Okay. So dihydrogen phosphate remove that iron. So what would happen if I brought this dihydrogen phosphate in and it removed the gold? Take the gold away, what's going to happen? Take a prediction. Is it going to get more gold? Is it going to get more colorless? Is it going to get more red? And just making predictions to start is always a good thing to do from the scientific method. Right? Okay, then next our question is, how does a mixture of reactants and products respond when you increase or decrease the concentration of a reactant, right? So that's essentially what we were doing. We were increasing the iron, we were going to increase the thiocyanate, and then we took away the iron, right? So we're increasing or decreasing a reactant. What's going to happen? And so I'm going to show you this video, and you're going to notice, I want you to note the initial color of the potassium thiocyanate, okay? And then I'm going to add 1, 2, 3, 4, 5, 6 different things. Okay, and I want you to just write down what color change you saw. And then from there, we'll just form a conclusion. Okay, now this video can be found on my channel, and you'll notice that it's me back in my classroom, which will bring back fond memories, hopefully. Okay, so here we go. Hi students, I'm back in the classroom here at Maricosta High School, and I wanted to do a quick demonstration for you to show how adding and taking away reactants and products can shift equilibrium position. So the reaction I'm going to do for you today involves these ions, and this is the net ionic equation that we see listed here. Notice it's at equilibrium, that both the forward and the reverse reactions can take place. And we're going to look for color changes in this petri dish here. Right now, there's a colorless solution of potassium thiocyanate in there. And the potassium is just a spectator ion. It doesn't actually participate in the reaction at all. And so let's go ahead and add a few things to the container, and we'll see what happens when we shift the equilibrium. Okay? All right. So the very first thing I'm going to do here is add just a few drops of iron nitrate. And this is actually iron 3 nitrate. So 1, 2, 3. And give it a swirl. Let's go a little bit here. And you can see that there's definitely a color change that happens here. And the next thing I'm going to do is add some potassium thiocyanate. So just a little bit of potassium thiocyanate. Just a little bit. And you can definitely see another color change there. It's going to keep the red color. You can record those observations. All right, next I'm going to add some potassium nitrate. Once again, this is potassium nitrate. Now, potassium and nitrate are spectator ions. So let's see if those spectator ions affect the equilibrium. Nothing seemed to happen there when we added spectator ions. All right, let's try something else. Now we're going to add some sodium phosphate. Sorry, I had forgotten the sodium phosphate back in the lab, so I had to run back to get it. Sorry, I had to grab the container. All right, this is sodium phosphate. I'm going to add just a little bit of this. This is my favorite part. Watch. This is my favorite part. Now you can close your eyes. Voila, it goes back to colorless. Pretty cool. It's not magic, it's science. All right, now I'm going to go back and add just one more drop of the iron-free nitrate. And I'm going to add just another bit of potassium thiocyanate. You can go ahead and make any observations. And I'll go ahead and give it another spoon. Just a little bit more iron nitrate actually. You can see the effects of shifting equilibrium. Okay. All right, you have a few questions about these observations, and then we'll go ahead and discuss those in an upcoming meeting. So, hope you enjoyed that and that it was helpful. Have a great day. Okay. So let's go back over and take a look at what those observations were and see if we can explain it. All right, so the initial color of potassium thiocyanate, I hope you were able to pretty obviously see that that was colorless. Okay, so potassium thiocyanate by itself, it's colorless. The first thing I added here was iron-3 nitrate. And the observed color change, you noticed, was that it got more red, okay? So in other words, if we look back up at our reaction here, if I added more of my reactant, I got more of the color of product. Let me write this down another way here. So remember this iron, stop sharing for just a moment. Okay, so the iron, the thiocyanate, and then we had iron thiocyanate. And we said this is gold, and this is colorless, and this is red. So the first thing we notice is that when we had a colorless solution and we added more of something that's gold colored, it actually got more red. This whole time we're just basically going to look to see if it's getting more red, that means it's shifting to the right. And if it's getting more colorless, it's shifting to the left. okay? So first thing we saw was that it got more red. When we add more reactant, it makes more product. That's kind of cool. All right, let's see. Let's go back there. Oh, and then what I had written disappeared. Go figure. Okay, let's fill this in one more time. So this was, I'm gonna choose another color here. I don't like red. I prefer UCLA. So colorless was the first thing. We added more iron thiocyanate or iron nitrate, iron trinic, and we see that it gets more. Then the next thing I added was potassium thiocyanate. Added another bit of reactant, right? Remember that potassium is just spectator. And again, we saw that it got more. All right, third thing that I added was potassium nitrate. And you probably noticed that nothing happened. Right? There was no color change. Why? Because potassium nitrate were both spectator ions. They're not participating in the overall reaction. So they didn't affect the equilibrium at all. Okay. The next thing we added was that sodium hydrogen phosphate. And sodium hydrogen phosphate takes away that reactant, that iron. And we noticed that when we remove reactant, it actually got more colorless. Now, I think I added a little too much of that because what was supposed to happen at the end when I added more iron nitrate and added more potassium thiocyanate, you probably noticed when I dripped a little bit of it, it got more red in there. But then when I swirled it, it got a chance to react, right? Actually collide. When you swirl or stir, those molecules can find each other, right? Think kinetics, so they can collide and react. And once I swirled it, then this hydrogen phosphate made it colorless again. I added a little too much of that. But anyway, you'll notice that when I initially dropped some more of the reactant in, it got more red again. And again, here, it got more red. Okay, so those are the observations I hope you made. Okay, we're just looking at shifts in equilibrium by looking at color changes. Okay, and so in conclusion, we want to decide, all right, let's see. We want to write in 2 sentences or less, describe how a system at equilibrium will respond when the concentration of reactants is increased or decreased. I can say that, that shifts in equilibrium observed color changes. That's why it got more red. And when removed, right, by that hydrogen phosphate, then so you just think of it this way. It might even be easier to think of it this way, where you think of colorless reaction in terms of colors. The reactants are colorless and the products are red, right? And so if I add more reactant, it got more red. If I take away reactant, it got more colorless, okay? And so this is kind of an interesting phenomenon. And essentially what I'm doing here, I'm gonna stop sharing so you can see me here. When I think of equilibrium systems, I like to think of those scales of justice where we have, reactants and products. And so if we're at equilibrium, it doesn't mean that we have equal amounts of reactants and products. What it actually means is that the rate of the forward reaction is equal to the rate of the reverse reaction. So I often think of those scales of justice. You probably see them in a like a lawyer's window sometimes. It's like this. And actually, this is in my that's not a very good drawing. Art was never my strong point. Okay, so if you think of this as reactants and this as products, those are the scales of justice, right? So if they're equal, it doesn't mean we have equal amounts, but just simply that they're at equilibrium, okay? We'll talk more about what this means in just a moment. But if you add more reactants, it kind of weighs down the scale like this, right? And so the response to that is to undo that stress that you just add, right? So adding reactants is what we call adding a stress to the system, or I stress it out by adding more reactants, and the response is to make more products to get back to equilibrium, okay? If I take away reactants, then what does that do to the scale? Well, if I take away the reactants, it tips the scale like this. And then so the response to get back to equilibrium is to make more of the reactants, right? And so we saw that in that if we added more reactants, it got more red. In other words, it made more products. If we stress the system by taking away reactants, it responded by making more and getting more colorless, right? And so that's really what I wanted you guys to just introduce you to, is this idea of what equilibrium looks like with chemicals, okay? Now let's go ahead and take a look at the notes we have today. I'll probably keep you a little bit over, but I'm going to go through these notes relatively quickly. We'll see. I'm not going to keep you too far over, but I did start late. So here, okay, let's share the screen and share this. That's not what I want. Where did my notes go? Oh, here they are. Okay. Again, you have access to these already. And if you want to write them in your brain book, it's not a bad idea, just because then you'll always have access to all of your chemistry notes in one place, okay? All right, you can always go back and watch this video again on YouTube if you want, or if you missed something or whatever. Okay, so chemical equilibrium, here we go. So reversible reactions. This is the first time we've seen reversible reactions. Essentially, we have forward and reverse reactions that occur simultaneously. Almost all chemical reactions are reversible to some extent. Not all of them, but many of them. So if the forward reaction looks like this, and then the reverse reaction just means the products can reform the reactants. And rather than writing both of them out like that, we just write this overall reaction with a two-way arrow like that, okay? So equilibrium is a dynamic condition. This is something that's really important for students to remember, okay? It's dynamic. Think about it. What does dynamic mean? Dynamic means it's not stagnant, right? In other words, the molecules are always moving. And I want you to keep that in mind when you look at that simulation tomorrow, okay? Remember that molecules don't have brains. It's not like they all just look at each other and go, hey, we've reached equilibrium. Let's all stop reacting now. No, that's not the way it works. Molecules don't ever stop moving. They're always going to have kinetic energy. They're always going to be colliding and forming products and then reforming reactants, right? The movement doesn't stop as long as they're, well, ever, because they never reach absolute zero, right? So there's always going to be some collisions happening, and some of those collisions are going to surpass activation energy if there's sufficient energy and proper orientation, right? So that they can react, right? So it's a very dynamic condition. So that word dynamic means in motion, okay? It's not stagnant. And there's two opposing changes that occur at equal rates in a closed system, okay? Now, a closed system means matter cannot enter or leave, okay? So you can't add or take away molecules or atoms, but energy can, okay? And so all of these phase changes that you're familiar with now are a very, very good example of equilibrium. In other words, you know, we know that at 0 degrees Celsius and standard pressure, ice melts at 0 degrees Celsius, but also freezes at 0 degrees Celsius. 0 degrees Celsius and 1 atmosphere is the equilibrium point between the solid and liquid phases for water. In other words, both will coexist at equilibrium at 0 degrees Celsius, which is why we keep our freezer below 0 degrees Celsius so that everything turns to ice, right? When you freeze something. Otherwise, you'd have some liquid and some ice. Or some solid. Okay, water boils at 100 degrees Celsius, but if you have a closed container at 100 degrees Celsius, you're going to have some gas and some liquid. If you take it slightly above 100 degrees Celsius, then it'll all vaporize. If you take it slightly below 100 degrees Celsius, it'll all turn back to liquid. But 100 degrees Celsius is both the boiling point and the condensation point for water. Okay, it's an equilibrium. They're two opposing changes that both exist in the same closed container. And then same for solid and gas, sublimation and deposition, okay? So which picture represents a closed system? Okay, that one's pretty straightforward, right? This one, matter can't enter or leave because the lid's on top. Here, if you imagine like a pot of spaghetti water on the stove when it's boiling, you know, the steam is coming out. And if steam's coming out, then that means you're losing matter, right? The steam is H2O molecules becoming a gas. So you're losing matter, and that's not a closed system. So it would have to have the lid on top to keep all the matter inside, okay? All right, so a closed system at equilibrium would be like a pot of boiling water with a lid on top. Now, here's the biggest misconception that students have about equilibrium. Because it has this word equal, or you know, almost spelled a little differently, but that word equal, students always think you have equal amounts of reactant and product. No, it's not equal amounts of reactants and products. It means that the rate of vaporization in this case is equal to the rate of condensation. So the two rates are equal and opposite, okay? So we've just studied kinetics, so you guys understand reaction rates now, right? So it does not mean that the amount of liquid is equal to the amount of gas, simply that the rate of vaporization is equal to the rate of condensation, okay? So even though the rate of forward reaction is equal to the rate of a reverse reaction, the concentrations of components on both sides may not be equal, okay? So in other words, why I might have a little tiny bit, only 1% of 100 molecules are A, only 1 out of 100 molecules are A, and 99 of the molecules are B, and it still reaches an equilibrium, okay? I could have the other way around, 99 A's and only 1 B, but it could still reach an equilibrium. Equilibrium means that you're not seeing an overall change in the amount of reactant or product. And I'm hoping this will become very evident and very clear to you in the simulation, okay? When you reach an equilibrium, the amount of A and the amount of B will be constant. They don't have to meet each other. They don't have to be the same. They just have to be constant, okay? So they don't necessarily have to have equal amounts of reactant and product. Okay, so we were just exploring Le Chatelier's principle. And Le Chatelier's principle states that when a system at equilibrium is disturbed by application of a stress, it attains a new equilibrium position that relieves that stress. And here's a picture of our Frenchman, Le Chatelier, who lived through the late 1800s and early 1900s. And basically, a stress is one of three things. So if you've got this nice equilibrium position, right? You've got a reaction at equilibrium. A stress is anything that's going to tip the scale one way or the other, okay? That's a stress. And then the scale or the system will respond to relieve that stress. So a stress is going to be a change in concentration, and that's what I was doing in the demo. I was changing concentration by adding more reactant or taking away reactant. Changing pressure or changing temperature is a stress, okay? Now, keep in mind that pressure will only affect things in the gaseous phase, okay? Only gases are affected by a change in pressure. Okay, so pressure, this is exactly what I just said. Pressure affects gases only. So increasing the pressure will always favor the direction that has fewer gas molecules, okay? So here's an example. This is the Haber process. This is a very, very common equation that's looked at in real life chemistry and the formation of fertilizers. Sorry, that I had a little brain fart there. Okay, so notice that on the reactant side here, where's my, there we go. Okay. This will work. Okay, on my reactant side versus on the product side. On the reactant side, if you notice, I have a total of 4 moles of gas, right? And so, right, 1 nitrogen and 3 hydrogens, right? So 4 moles on the reactant side. And on the product side, oh, I lost my mouse. Where'd it go? Oh my goodness. My mouse disappeared. On the product side, I have 2 moles of gas. This is supposed to be on the product side. I'm so sorry, you guys. This technology is nuts. It's supposed to be over on the product side, 2 moles, okay? And here's the way I want you to think of this is, let's say, okay, so if you increase the pressure on a system of gases, they're gonna get more crowded. And gases, like humans, don't like to be crowded, right? I have something to admit. I've never taken my kids to Disneyland. Why? Because I hate crowds, okay? I've got to find the perfect day to go when it's not crowded. So humans don't like to be crowded, and gas molecules don't like to either. So if you increase the pressure on those gases, and remember our PTV card, we can increase the pressure by lowering the volume, right? So if I decrease the volume, those gas particles get crowded and they don't like it. They shift to the side with fewer gas particles, okay? And then if you do the opposite, if you increase the volume or decrease pressure, they're gonna be like, yeah, we got plenty of space. Let's call up our friends, more the merrier. Here's my analogy for you. Let's say that you are sitting at home on a Saturday night and we're not in quarantine, and you get a phone call from a girlfriend or a friend in Hermosa Beach, and she's like, hey, I am at this party, and it's in a 1-bedroom apartment, and it's right on the Strand, and there's like 100 people here, and it's so much fun. And you're gonna go, and she's going, come over. And you're going, that doesn't sound like that much fun, right? 100 people crammed into a 1-bedroom apartment. Yeah, no thanks. I'll pass on that. But if you get a phone call from a friend who's like, hey, I'm on this sweet mansion out in Manhattan Beach. There's 100 people here. This place is huge. There's 7 bedrooms. It's enormous. Come on over. You'd be like, oh, the more the merrier. Let's go, right? So if there's more space and we're not going to be crowded, we're more likely to go over there. Same thing with gas particles. Think of it that way, okay? Gas particles don't like to be crowded. So if you increase the pressure on them, that stress is going to make them shift to the side with fewer gas particles. And if you relieve the stress, they're going to think the more the merrier, and they're going to shift to the side with more gas particles, okay? All right, I don't know what I did here, but I can't find my mouse, so let's see. Oh my goodness, everything is... I am at a loss here. Everything is... Does anyone have an idea of how you like stop everything in this? Now it's just making more text boxes for me all over the place. I don't know what to do. Oh, whatever I did just did something. Okay, now I found my mouse again. Here we go. Okay. Can you guys still see this screen? With
no.
My slide? No. Okay. Let's see. Let's do this. Okay, I think it's going to work. Okay, just a couple more slides and we're done. All right, so there we just did this. Increasing pressure will cause it shift to the right with fewer gas particles, so they're not as crowded. Decreasing volume will also cause a shift to the right, because remember, volume and pressure are inversely proportional, okay? And we're talking about gas particles. Okay, and then the opposite would cause a shift to the left, okay? All right, temperature changes. And you guys are gonna watch a video tomorrow of myself in my kitchen doing a demo with temperature changes. Okay, so you'll see another example, a real life example of this with chemicals tomorrow. Increasing temperature will favor the endothermic reaction. Decreasing temperature favors the exothermic reaction. So let's look at an example. Here's one that you probably recognize, liquid turning to gas. And obviously, we need to add heat to a liquid to make it turn into a gas. So this is endothermic in the forward direction, right? And let's say this is at 25 degrees Celsius, okay? So now, if I increase the temperature to 50 degrees Celsius, think of heat as a reactant. So think of it again like my little scales of justice here, right? If I add more heat, that's like adding more reactant. The stress tips my scale this way. And so you're always going to say what the response is. The shift is the response to get back to equilibrium, right? So I have to shift a little to the right to get back to equilibrium when I add more reactant, okay? Let's try this one. The forward reaction becomes favored till we reach a new equilibrium. And I'm going to increase the amount of gas, which makes sense. If you heat up liquid water, you're going to make more gas, right? If I do the opposite, where I take away the heat, I take away reactant, that stress tips my scale this way, right? And then to relieve that stress, I'm going to have to shift to the left to get back to equilibrium. In other words, if I cool down this system, more of the gas is going to turn back into liquid water, which makes perfect sense, right? The reverse reaction becomes favored. So it'll always get back to equilibrium. It's just that a new equilibrium position is going to be reached, okay? And I'm actually going to stop there for today because I don't want to go too far over on our time. So here's what I'm going to do. I'm going to stop there. I'm going to and let you guys just work you know, understanding Le Chatelier's principle right now. I'll put a couple of worksheets up for you guys to try. And then when we come back together on Friday, I'm going to teach you how we quantify this position of equilibrium, okay? So that's all I've got for you today. We just have one more slide, and we'll go over this slide on Friday. I don't want to overwhelm you right now with too much, okay? Let's just focus on Le Chatelier's principle for now, okay? So let's see if I can, I don't know, do we want to, we're a little over on time. Do we want to do an example here? Or I think I'll put the worksheets and I'll put the answer keys up. If you guys have questions, let me know. I'll also put up some videos from Mr. Anderson that'll explain the same thing. And so hopefully with the videos and the worksheets and the answer keys, it'll all start to make sense. But if you just think about this, you know, this scale shifting one way or another, I think it should help. So just remember, the stress is whatever's tipping the scale one way or another. And then the response that you record is always the shift to get back to equilibrium. Okay? All right, guys, I'm going to stop there for today. And I hope you have a lovely day. Thank you for coming. I'm going to pause the recording.